Last tutorial of the unit on sequences and series is infinite geometric series. An infinite series is a series with an unlimited number of terms, and we represent that with n equals infinity. Thus, a geometric series that goes on forever is called an infinite geometric series. Infinite goes on forever, geometric series. And it is donated by s theta, not s of 4, not of s of 6, not s of n, where n is a finite number, but s of theta. An infinite geometric series can do two things, can be two things. It can be convergent, and convergent means when you figure out what is the sum of infinite geometric series, it converges, it goes to a number. Or it can be divergent. Divergent really means it goes to infinity. And when you think about it, if you added a bunch of numbers together, well, wouldn't that get really, really, really big? And that's one of the key things we're going to look at. When does something converge to a number, and when does something diverge to infinity? So here's a little exercise, and if you want to pause the video and do it yourself, you can. You are going to use a formula from your homework for the other day, and again, if this were a question from last day, you would decide which formula you would use to figure out the sum of these two series, and again, they are geometric. This one right here, r is equal to 7, and this one right here, r is equal to, what's r equal to? 0.5. So r is equal to 0.5. So 0.05 divided by 1 is 0.5, and 0.025 divided by 0.05 is 0.5. So again, you might pause the video and use your first formula, because we know what n is. Remember, in our two formulas from geometric series, one of the formulas is when we knew n, and the other formula is when we knew the last term. And we don't really want to figure out the last term, especially the 100,000th term. So pause the video and use your first formula where you know n, and figure out what is s of 5, what is s of 10, what is s of 100,000. Probably need your calculators for those ones. And then after you've calculated those, let's see what we see. Okay, so hopefully you've done that, and I'm not going to show the calculations because you should have gotten these numbers with the formula. And here's the numbers I got. And this one was so big, I couldn't figure it out. So I'm going to call it infinity. So when you figure out the first 100,000 terms of that series, the number is huge, and you might have got an overload message on your calculator, but it got really, really, really big. On this one over here, my first one was this. My second one was this, which is really just a little bit bigger. The 1 and the 9, the first two digits lock in, and the difference of the other ones is very small. But when I did this one, I get that, which again is very close to 0.19, right? 0.2 is 0.1 more than 1.9. So in these two series, this one on the left is what we would call divergent. Again, it does not go to a finite number. It doesn't get closer and closer and closer to a finite number. In fact, it gets really, 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 really big. And this converges. If we looked at these numbers, 0.19375 is pretty close to 0.2, but 0.1998 is really close to 2. And if we did S of 20 or S of 100, it would even get closer. So this is a convergent series. And what you might notice is when R is less than, or sorry, when R is less than 1, as in this one up here, when R is 0.5 here, and this is just one example, but it will be true. When R is less than 1, the series is convergent. Now, when we say R is less than 1, really what it is the absolute value of R. And the absolute value just means that it can be positive or negative. So the absolute value of 4, for example, is equal to 4, but the absolute value of negative 4 is also equal to 4. So the absolute value can be thought of as the distance away from 0. And when we talk about distance, you don't talk about positive, you don't talk about negative. It doesn't matter if you go left or right, you're still going X amount of steps. So R was 0.5, which is obviously less than 1, but it's in this window. So the other way you can think of the absolute value in this range right here is as long as R is greater than -1 or less than +1. And that's what the absolute value this picture is going to represent. It's going to picture this thing right here. And whenever this happens, when R is in between -1 and +1, you get a convergent series, and you always will. When R, the absolute value of R, is greater than 1, you get a divergent series. And it goes to infinity. It always will. So when R is, let's call it, when R is greater than 1, or R is less than -1, we're going to get a divergent series. So as long as R is not in between -1 and +1, this series, when we add it all up or when we determine it, it's going to go to infinity. Okay, so here's that important statement right here. So in looking at infinite geometric series, it seems that the common ratio is the most important thing. And if we determine that the ratio is in these two different cases, then the answer becomes very simple, and we have a formula for that. So here's a couple of examples where we want to figure out the infinite geometric series, adding an infinite amount of numbers, and we're going to plug into our formula, and we're going to see what we see. So again, R is -7/12, which is in between, which is in that area. It is greater than -1 and less than +1, so that's good. So we end up with T1 over 1 minus -7/12, which is equal to 144 over 1 plus 7/12, which turns out to be 19/12. And when we do that final calculation, here's what we get. That kind of nasty decimal is what these infinite amount of numbers will converge to and add to. Now, in the second example, what I want you to notice is R is 4/3. R is greater than 1. So this is a divergent series. This will go to infinity. It might take it a long time to get to infinity, but it will go to infinity. If you blindly applied your formula, you would have, okay, the sum of an infinite number of terms is equal to T1 over 1 minus 4/3, which is equal to -4 over -1/3 which is equal to 12. And you would say that the answer is 12. You use the formula. But again, because r is greater than 1, s of infinity equals infinity. So when we've been doing our calculations this unit, we've always wanted to find the common difference. We've always wanted to find the common ratio. And an infinite geometric series really highlights the importance of that. So let's just do a few examples illustrating where these kind of questions pop up. So here's our first example. Express 0.25 repeating as a fraction using an infinite geometric series. You might have learned another way to do this kind of question, but we're going to use a series here. So 0.25 repeating is equal to 0.25252525, etc. And that's really equal to 0.25 plus 0.0025 plus 0.000025, and so on. I'll do one more. So again, for infinity, right? An infinite number of fractions. So we can rewrite this as a series. So we'll have 0.25 plus 0.0025, etc. I'll just do one more. And again, to go from one term to the other, we are multiplying by 0.01. So in our example right here, and again, if you want to see where the 0,1 comes from, we have this divided by this, right? And there's our 0.01. So in looking at our R is obviously in between -1 and +1. And then what illustrates is we can use our infinite series. So T1 is 0.25. And we get 1 minus 0.01, which is equal to 0.25 over 0.99. And if we simply multiply top and bottom by 100, move the decimal place 2 places to the right, there is our fraction, 25 over 99. Now, if you have a button on your calculator that changes decimals to fractions, this is the answer you're going to get. So that's kind of an interesting one that might be useful for younger kids when they're doing their fraction decimal stuff. The sum of an infinite series is 105, and the common ratio is -2/3. We want to find the first term. So first of all, this makes sense, right? If the sum is a finite number, something's converging to 105, then the ratio has to be between -1 and +1. And -2/3 is between -1 and +1. I mean, simply on a number line, here's our 0, here's our 1, here's our -1, and -2/3 is right here. So here's this part of the number line we want, and there's our common ratio fits in it. So again, with our formula, we have a formula with three parts to it, and as long as you know 2 out of those parts, you can go ahead and use the equation and solve that particular question. So we know S of infinity, we know R. The only thing we don't know is T1, so we can go ahead and use it. So S theta is equal to S infinity is equal to 105, and R is equal to -2/3. In our formula, then, we're going to plug in our parts. We're going to simplify. We're going to get 5/3. And now we're going to go ahead and solve this equation. So this says T1 divided by 5/3. You can simply undo a division with a multiplication and follow the golden rule. So a 5 on 3 on the top and a 5 on 3 on the bottom cancel out, and we end up with T1 is equal to 175. And now, in order to find T2 and T3, well, again, all we have to use is our common ratio. To go from here to here, we're going to multiply by negative 2/3, and from here to here, we're going to multiply by negative 2/3. And when you do that, you get negative 116 and 2/3 if you wanted to make it a mixed fraction, and 77 and 7/9. So again, key idea is, what is r? And if r is greater than 1 or less than negative 1, the answer is super easy. It's infinity. So here's one last question. A rubber ball dropping from a height. So if you think what's going to happen with this ball, it's going to bounce, and it's going to not bounce back as high, and then it's going to go to the ground, bounce again, and not come back as high until finally it's going to stop bouncing altogether. So I'm just going to draw that picture over here, because a picture is really important in understanding what's happening. So here's our 32 feet right here. The ball's going to start off at 32 feet, and it's going to bounce to the ground. And then it's going to bounce back 60%, a little over half, and it's going to go back down. And it's going to bounce 60% of that, and it's going to bounce back down, and et cetera, until finally it stops. So in this case right here, when we figure out like how far it goes, well, first of all, it has to go to an answer, because again, it's not bouncing back to its original height forever. It's not bouncing back higher, where the ball keeps going higher and higher, going to infinity. So given that the ball will eventually stop, it is a convergent series, and there's a couple of pieces of information on here. The drop from a height of 32. Well, that's your T1. That's the starting point. That's the first piece of information. And the other valuable piece of information, it bounces back to 60% of its previous height. And that's our repeated idea. That's our common ratio. And we can express it as a decimal, or we can express it as a fraction. But given that the absolute value of r, 0.6, is less than 1, and it's greater than negative 1 and less than positive 1, that tells us there will be a convergent series. So I'm just going to I've done a quick couple of calculations. So when you multiply 32 by 0.6, here's what you get, 19.6. So the ball is going to bounce up. After it hits the ground, it's going to bounce up to 19.6. And its next bounce is going to be 11.52. And then it's going to go down again, and then et cetera. So I'm just giving you the first three pieces of information. But here's the key thing about the picture. It's asking for the total distance. So look what's happening. The ball is going down, and then the ball is going up, and then the ball is going down, and the ball is going up, and the ball is going down, the ball is going up, et cetera. So we have this. Our total distance has two parts to it. It's the down part, so I'll call it the down direction. But there's also this part to it. Then the ball starts going up. Then the ball starts going up, then the ball starts going up. So there's also the upward direction. And we have to figure out these two parts. Now, the nice thing is they're very similar, and it's this notion of, well, if we start at 32, it goes down, then it goes down another 19.6, and then it goes down another 11.52, and so on and so on. So there's this infinite down series in here, along with the infinite up series, but they start at different places, and that's what's important to understand and draw the picture. So our downward calculation would be s of infinity of t1, which is 32, 1 minus 0.6, but our up direction would be not 32 because that's not where we start our first up calculation. We have to go up to 19.6, and then they are the same. And when you figure out what those equal, they equal 80 and 48 respectively. So this ball in this story will bounce a total distance of, and up and down are different directions, 128 meters.